Hello and welcome to Mathematics Illuminated, where I shed light on any and all math topics from simple to advanced in a way that's easy to understand and interesting to learn. Please subscribe to my channel as I continue to post more videos and comment below on videos you'd like to see in the future. This is part 7 of a series I have on complex numbers. In this video, I'll go over representing trigonometric functions using imaginary numbers. If you haven't seen the other parts of this series and would like to check them out, I'll leave a link to them in the description. In this video, I'll answer the questions: how can trigonometric functions be represented using imaginary numbers, and how do these representations help define hyperbolic functions? Euler's formula, as discussed in part 4, states that e to the xi equals cosine x plus sine xi. What I'll do now is try and raise e to the negative xi instead. You'll see why soon, don't worry. This expands to cosine negative x plus sine negative xi. Trying to find the cosine of a negative variable leaves you with the cosine of the variable, and trying to find the sine of a negative variable leaves you with the negative sine of the variable. Here I'm showing this with the variable theta, representing an angle on the unit circle here. As I discussed in part 4, cosine and sine can be defined as the x and y coordinate of where the angle intersects the unit circle. Looking at negative theta here, we see that where it intersects the unit circle, it still uses a positive x coordinate, but uses a negative y coordinate. And so the cosine of negative theta is just the cosine of theta, and the sine of negative theta is just negative sine theta. Plugging this back into what we have here, we know that e to the negative xi is cosine x minus sine xi. And so we can use these two formulas to do something interesting. What we'll do is add them together. If we do that, we notice that the two sine values, sine xi and negative sine xi, cancel out. And we also notice that the two cosine values can be added together. And so we are just left with 2 cosine x. Then what we can do is divide both sides of the equation by 2, and then we now have a new representation for cosine. Additionally, we could also subtract e to the xi and e to the negative xi instead of adding them. This change would cancel out the cosine values and leave us with 2 sine xi. Seeing this equation, we can then divide both sides by 2i, and now we have a new representation for sine as well. These two representations for cosine and sine are very important to complex number theory because they can allow one to take the cosine or sine of any number, real or complex, and then express and approximate the values. Tangent is defined as sine over cosine, and here we can plug in our new definitions for sine and cosine. Then we can multiply both the numerator and denominator of this fraction by 2i, getting this. Then we can multiply both the numerator and denominator by I, which gets this, and then expanding the negative into the numerator, we have our final simplification. And here you can see the cosine, sine, and tangent all defined using imaginary numbers. Let's show an example of it coming into use. Here I'll find the cosine of I using this definition. We see that in the exponents of our definition we get I squared, and then simplifying we get a final answer of 1 plus e squared all over 2e, which is a real number. If something seems familiar about all of this, it's because you may be familiar with hyperbolic functions. What you may not have known about hyperbolic functions, though, is that they can actually be represented by cosine, sine, and tangent of imaginary values. Like the trigonometric functions they are based off of, hyperbolic functions result in real numbers when you plug a real number into them. They are represented the same way as trigonometric functions, except they have an h at the end. These are the graphs of the hyperbolic functions as shown color-coded here. And that brings me to the end of this video. It was a bit of a short one, but definitely covered useful information regarding complex numbers, as the representations of trigonometric functions with imaginary numbers will often show up in complex number theory, and seeing how they can help define hyperbolic functions can help widen your understanding of how math concepts often tend to connect to each other without many realizing it. Please subscribe to my channel and like this video. Farewell for now.